Hello and welcome to my talk, which is on a local singularity analysis for the Ricci flow. And the main results that I will present today are joint work with my PhD student Gianmichele Di Matteo. So let's jump right in. The goal of this talk is I want to introduce a refined local singularity analysis for the Ricci flow, which investigates curvature blowups locally. And in particular, we want to localize or generalize results of Jörg Enders, Peter Topping, and myself, and a result of Natasha Sesum. And all of this is done by introducing new definitions of type 1 and type 2 singular points in a Ricci flow and introducing new regularity scales. So before we do all of that, I will give you a bit of a background introduction on what is Ricci flow, what it is good for, and how singularities happen in Ricci flow and how traditionally one classifies them into type 1 and type 2 and how one analyzes these singularities. Okay, so what is the Ricci curvature first of all? If you have a Riemannian manifold Mg, so G is the Riemannian metric, then of course we have the curvature tensor or the Riemannian curvature tensor, which essentially measures the difference between taking derivatives first in direction x and then in direction y, or the other way around. And then the Ricci tensor is a trace of this Riemann curvature tensor. So the Ricci tensor has various good properties. It measures the distortion of volume compared to Euclidean space. That's where it appears. It's also a very crucial quantity in Einstein field equations, so it's of huge relevance to general relativity. And in particular, it has this nice formula in harmonic coordinates that the Ricci tensor is essentially minus a half the coordinate Laplacian of the Riemannian metric plus some lower order terms. Okay, and this is important for us, so we really think of Ricci as minus 1/2 the Laplacian of the metric in the following. Okay, so some examples on a sphere. Of course, the sphere is the round metric. We have that the Ricci curvature is positive. On Euclidean Rn with the Euclidean metric, we have Ricci curvature equal to 0, and Ricci is negative, and by negative I mean negative definite, so it's a 2 tensor on hyperbolic space. Then we also define the scalar curvature, which is just a trace of this Ricci curvature. So these are all standard notions in differential geometry. Now what can we do with that? So Hamilton in this should of course be 1982, not 1892, little typo there. So in 1982, Hamilton introduced this Ricci flow equation, which says that we have a Riemannian metric on a manifold, and this metric evolves in time, and the time derivative of the metric is minus 2 times the Ricci tensor. So if you remember that the Ricci tensor was minus 1/2 the Laplacian plus some lower order terms, then this basically gives us that the metric evolves by time derivative of the metric is equal to Laplacian of the metric plus some lower order terms. Okay, so in some sense this is a heat equation, but now we have to be careful because this is a very nonlinear heat equation, because of course the Laplacian on a manifold depends on the metric. So actually the coefficients of the Laplacian evolve as well when the metric evolves. Okay, so the Ricci flow usually is called to have an initial metric, which I call G0, if it just exists on a time interval that starts at 0 and goes up to capital T, and capital T could be plus infinity or could be some finite time. Okay, and as I just said, this is a system which is roughly a heat equation, but it's non-linear, it's quasi-linear, and it's weakly parabolic, and of course it's a system of second order. Okay, so systems of this equation, of this type of equations, have some good properties, and the good properties are that we have short time existence and we have some short time smoothing effects. So we can start the flow with certain manifolds or orbifolds or metric spaces, and we have good initial conditions, and we have some smoothing of the curvatures. But then we also have a bad property, which is that singularities in finite time are everywhere. In particular, if we start a flow that has positive scalar curvature everywhere, then we necessarily must have a singularity in finite time. Okay, let's look at a few examples in low dimensions. So if we take dimension 2, then the Ricci tensor is just the Gauss curvature times the metric. So the Ricci flow becomes time derivative of the metric is -2 times the Gauss curvature times the metric. Okay, now if we are in dimension 2, we can write the metric in a very nice form. We can write it in isothermal coordinates. And then basically the whole metric is fully determined by some conformal factor, which usually one writes as e to the 2u, but we can also write it just as a capital U of t. And now if the metric evolves, that means just that this factor, this conformal factor, evolves. Okay, and the Ricci flow equation translates to these equations for either the conformal factor little u or for the capital U. Okay, now in this we actually really see the nonlinearity of the equation. So this is not a standard heat equation. This is really a nonlinear equation. The second of these equations, the one for capital U, is usually called the logarithmic fast diffusion equation. So the Ricci flow in dimension 2 becomes the logarithmic fast diffusion equation. Now we can start with any manifold, and the Ricci flow, or at least a normalized version of it, where we rescale at every time to keep the volume fixed, behaves very nicely and converges to a metric of constant curvature. So we can actually use the Ricci flow to reprove the uniformization theorem. Okay, let's move to higher dimensions. So if M is a closed, and by closed we mean compact and without boundary, a closed three-dimensional manifold, then if M has positive Ricci curvature at the start, at the initial metric, then what happens is that the metric shrinks everywhere, and the whole thing shrinks to what is called a round point. Or again, if we look at the normalized version of that, then the Ricci flow converges to a round metric, so to a round sphere. And that's Hamilton's sphere theorem of 1982. Okay, if instead we don't have positive Ricci curvature at the initial metric, then we might experience also local singularities. So in the first case, we have this global singularity, everything shrinks to 1 point. While here, we can also have local singularities. And the idea is, if you start with something which is shaped like a dumbbell, then you have this neck-like region, which looks like an S2 in a cross-section times some interval. And then because the S2 has enough positive curvature, then even though it's possibly slightly negatively curved in this direction of the interval, the positive curvature will dominate and the neck will shrink. And we see that we get this local singularity in the center of the neck. Okay, while these parts on the sides where the curvature is less large will prevail and will remain smooth. Okay, so the singularity happens only locally and not globally. Using a topological search reconstruction in this case, Perelman managed to prove both the Poincaré and Thurston's geometrization conjecture, and a crucial ingredient was understanding exactly this type of local singularities. These local singularities, as in the picture, are usually called neck pinch singularities of the Ricci flow. Okay, to understand this now a little bit better, we will look at a few pictures of Ricci flows. And the pictures that I will show you, they're not actually precisely computed simulations, but they're more kind of artists' impressions of Ricci flow. So they're not up to scale. Okay, here we have a sphere, and what happens to the sphere on the Ricci flow is that it just shrinks to a point. So the illustration is done this way, that the darker the color, the higher the curvature. Of course, the smaller the sphere gets, the larger its Ricci curvature becomes, and the faster it will shrink, and it will just shrink to a point. Okay? Next picture. Here we see a cylinder under the Ricci flow. So also the cylinder has a cross section that is a sphere, so it's drawn more or less two-dimensional, but the cross section needs to be at least a two-dimensional sphere. And then what happens is that it just shrinks while not changing its shape. And here we have this neck pinch singularity. So we have two large parts that are connected by this small neck region, and you should think this is at least dimension 3, so this is only a two-dimensional impression of a 3 manifold, and the central neck shrinks and in the middle collapses and becomes singular. Okay? Good. So let's look at a few symmetries of the Ricci flow. So given some Ricci flow, we have the following symmetries. So the first one is obvious, which means we can just shift the time, and that means we have a new time interval on which the Ricci flow exists, but otherwise it's the same Ricci flow. Then we have a second one, which is diffeomorphism invariance by diffeomorphisms in space. Okay? And the third is the most important symmetry, which is a parabolic scaling invariance, which means on the one hand we do scale the metric, so we multiply the metric with some lambda, and we also scale the time by 1 over lambda. So that means if lambda is becoming very large, we scale up, we make things larger, and the time interval on which the flow exists becomes also longer and longer. Okay? And we use this third symmetry to produce so-called blow-ups of Ricci flows. So if you have a sequence of times and we have a sequence of parameters lambda that goes to infinity, and we have some points in M, then we can define the sequence of pointed rescaled Ricci flows where the metric is rescaled exactly using this parabolic scaling invariance and also some translational invariance. So we blow up the metric and we divide by lambda k to get a slower time evolution in a certain sense. And then we try to take a limit of that. So geometrically what this corresponds to is we zoom in to a certain point, pk, or we zoom in to some singularity which happens at the limit of these points, pk, tk. Okay? And let's look also at the picture of this. Okay, here we have our neck pinch solution, and what we do is we just fix the scale in such a way, we blow up in such a way that the neck in the center has a fixed size. So that means the entire object becomes larger and larger and longer. The neck, instead of shrinking, just keeps its shape, keeps its size, and what we get in a limit is we get a cylinder. So we get this self-similar solution that we have seen before, this self-shrinking cylinder as a limit. Hamilton has shown that we have always a curvature blow-up on a closed manifold if we encounter a singular time. So meaning we can continue the flow smoothly unless the maximum of the norm of Riemann blows up, and it blows up at a specific rate, which is a constant 1/8 times 1 the remaining time to the singular time. Okay, and this result has then been extended by Ricci in '89 to show that it also holds for Ricci flows that are complete and have bounded geometry for every time slice. So that means for each time we have bounds on all the curvatures and their derivatives and on the injectivity radius. Okay. Hamilton then distinguished two types of Ricci flows. One is the type 1 Ricci flow, where in addition to this lower bound, we also have a similar upper bound of how the maximum of the Riemann tensor or the norm of the Riemann tensor looks like. So for some constant we have a corresponding upper bound. If we don't have such a corresponding upper bound, then this is called a type 2 flow. Okay, and let me just say the pictures that we have seen before, the sphere and the cylinder and this neck pinch, they're all of the first type, so they're all type 1 flows. If we want to construct a type 2 flow, we can do so by looking at what is called a degenerate neck pinch, where the two dumbbells do not have the same size. So let's also look for a second at a picture of this. Okay, here we have this degenerate neck pinch. So notice that one of these spherical bits is smaller than the other and is therefore more highly curved and shrinks faster. And we can organize this in such a way that it shrinks at the same time as the neck would shrink. So this side completely collapses, and basically we, in the limit, see half of the neck that we had before in a certain sense. So that's a so-called degenerate neck pinch, and that's an example of a type 2 singularity. Okay, let's now look at these two results that we want to generalize. So as I said, one is a result of Natasha's sum. So Natasha's sum proved for closed manifolds the following extension theorem. She showed that if one has a Ricci flow along which the Ricci curvature stays bounded, then we can always extend the Ricci flow. So we cannot have a singularity if the Ricci curvature stays bounded, or in other words, if we do have a singularity, then the maximum of the Ricci has to blow up towards this singular time. This result was later extended to complete bounded geometry flows by Ma and Cheng, and further extended by Bing Wang in 2012 to say that actually we have a singularity on a closed manifold at least, if and only if the Ricci curvature blows up, or the maximum of the Ricci curvature blows up. Again at this kind of type 1 rate, so we have a lower type 1 bound for the maximum of the blow up of the Ricci. Okay. Now an open question is, what can we say about scalar curvature bounded? So can we extend the flow if the scalar curvature is bounded uniformly on some time interval? And it is known that this is true if the dimension is 2 or 3. So in dimension 2, this is clear because the whole curvature tensor is fully determined only by the scalar curvature. In dimension 3, this is a bit more surprising, and it is due to what is called Hamilton-Ivy pinching. But it is expected that in higher dimensions one can find counterexamples to that. And some people say the first counterexamples might already arise in dimension 4, so that's the more pessimistic view. And some people believe that counterexamples might only appear in dimension 8 and higher. That's the more optimistic view. But basically everybody expects counterexamples, although so far no explicit counterexamples have been constructed. Okay, the other result that I wanted to generalize or localize is a result that I proved with Jörg Enders and Peter Topping. So back then my name was still Reto Müller. And it says the following. So we have a point, we call it singular, if for every neighborhood of that point, the Riemann tensor in that neighborhood blows up as we approach the singular time. Okay, so it's not enough to just say that at a fixed point the Riemann tensor remains bounded, but we want it to be bounded in a whole neighborhood to have a regular point. As I said, if we don't have such a neighborhood, so if on any neighborhood the Riemann blows up, then we call the point singular, otherwise we call it regular. Okay, and then we also have another definition we call a sequence which converges, pk converges to the point P, and the times tk converge to the singular time capital T. We call this an essential blow-up sequence if the Riemann tensor blows up along this sequence. Okay. Then we define limit flows. So limit flows are exactly the limits of these pointed rescalings. So we rescale as we have done before. We multiply with factors lambda k, and we scale down the time with 1 over lambda k. And we do this along a sequence which converges to pt. And in case that we can do that for the sequence just being the fixed singular point and the fixed singular time, then we call the flow a tangent flow at this point. Okay, in this result from 2011, we proved two theorems. One says if we have a global type 1 assumption, then for every sequence of rescaling factors lambda going to infinity, we can extract a limit flow, so we get this tangent flow, which exists now for all times from minus infinity to 0, and this flow has a gradient shrinking soliton structure. So what does that mean? That means it evolves self-similarly under the Ricci flow. So the only thing that happened to it is it scales with a factor minus t, and it might also move in a direction of a diffeomorphism. Okay. In particular, the shrinking sphere or the shrinking cylinder are two such gradient shrinking solitons. So there are these self-similar solutions. In these two examples, these diffeomorphisms don't exist, so we can drop them and we just scale. But in a more general case, these diffeomorphisms might be necessary. Okay, so we say that any limit flow or any tangent flow is a self-similar solution to the Ricci flow. Moreover, we know that these tangent flows are flat if and only if the point is a regular point, and in this case they're actually given by the flat Euclidean space. A second theorem says that if we have a manifold as above, that means it's evolving by a Ricci flow, and we have a type 1 assumption, so important. We also here need a global type 1 assumption. Then the following are equivalent. So P is a singular point. That just means there exists an essential blow-up sequence for this point. Or, equivalently, the Riemann at P and time little t blows up by some constant over the remaining time to the singularity. So that means we can pick actually for our essential blow-up sequence pk always equal to p for every k. And moreover, we have a blow-up of the curvature, not just any blow-up, but at least this type 1 rate, so a lower type 1 bound. And we can also show the same with the Ricci curvature, so also the Ricci curvature blows up with a type 1 rate, and also the scalar curvature blows up with a type 1 rate. So again, all of this assumes an upper type 1 bound, so a global type 1 assumption. And under this assumption in particular, we see that none of these curvatures can blow up at a lower rate than type 1. So a priori one might think that one of these curvatures might go to infinity, but not satisfy such a lower bound. But that cannot happen under a global type 1 assumption. Okay, so these are the results of Natasha Sesum and of Anders Topping and myself, so theorem A, B, and C. And what we want to do is we want to localize or generalize these results, and in particular, we want to get rid of this global type 1 assumption.